Okay, so we have this function here. How do we know which one of these functions it is? Well, it's an exponential function, right? So that means it's basically a number to the power. Now, because we're at 0, 3, 3 is called the what? 3 is the initial value. Okay? Now, I'm thinking, if I'm a guessing man, it's probably A. Now, how do I check and see if it's A besides typing that equation into my graphing calculator and graphing it? Put in this point and see if it works. Is 15 equal to 3 times 5 squared? And the answer is no, it is not. Okay, so then we have to look at this one. Okay, because it also has an initial value of 3. Is 15 equal to 3 times 5 to the 2 over 2 power? 3 times 5 to the first. Well, 3 times 5 is 15. That checks. Now, if you were a little leery and say, I'm not sure about that, well, you can go ahead and put the answer in here. And it works for here because 15 is equal to 5 times 3 to the 2 over 2. So it does work for there. And here, if we put in 15, that is not equal to 5 times 2 to the 1/2. So that didn't work, that didn't work. So it worked for here, so why do I know this is the answer versus this? Well, you can also try the 0, 3 in there. If you put 0 in for x, 3 to the 0 power is 1, and 1 times 5 is 5, so it should be 0, 5, not 0, 3 if B was correct. So that's why knowing that initial value helps me from the start. Okay, there we go. Match a function. Okay, 5, y equals 5 to the x would be a function that looks like this. Okay, that sort of thing. So if it's 5 to the negative x, what does the negative x do? Flips it across the y-axis. Flips it across the y-axis. So then all of a sudden it looks like that. What does the -1 do to it? Moves it down by 1. So we need it like this, down by 1. It should be A. Okay? If you want to check, put a -1 in for x. What's 5 to the negative of the -1? Well, that's 5 to the first, right? -1 is 4. So if we put in a -1, we should be somewhere up at 4. If we put in a +1, what's 5 to the negative first power? 1/5, right? -1 is a -4/5. So at +1, we should be down at -4/5 somewhere. This graph doesn't so totally accurately show what's going on, but it's pretty good. Okay? So the graph must be the same shape as 5 to the x, and it's reflected over the y-axis and shifted down 1 unit. Okay? All right. Is this an exponential growth or exponential decay problem? Decay because it's in between 0 and 1. Okay? So if it's an exponential decay problem, it's basically going down like this, right? Okay? So as we get closer to negative infinity, where is it going? Up to infinity. Okay? Going up to infinity. Does that, as we get closer to negative infinity, so -5. Ooh, no, something's wrong. Yeah, that's right. Because 0.9 raised to the um, 0.1 power. What's 0.9 raised to the 0.1 power? Somebody on your calculator. 0.98. And what's 0.9 raised to the 0.0001 power? 0.999. So this is actually getting really a lot closer to 1. Okay, it's getting closer to 1 there. And as we go towards infinity, what's 0.9 to the 10,000th power? Really close to 0. So it's basically going from 1 to 0. Okay, so it's going down, but not a whole lot. Okay. All right, the number of bacteria in a petri dish after T hours is this. Okay. What's the initial value? You can see it right in front of you. What's the initial value? 900. The initial value is 900. Because anything to the 0 power makes all this stuff 1. And 1 times 900 is 900. Okay? There are how many present after 5 hours? Well, you slip the 5 in right there. So you take 900 e to the 0.696 times 5 power. Type that all the way in exactly the way it is in your calculator. And then we're going to round it to the nearest whole number. And how many bacteria are present after 5 hours? Is it more or less than the original amount? More. So how many are there?
29,214.
29,214 to the nearest whole number. Yep. Number 3, I was wrong. I was right initially, but then I thought about it and changed my answer, and I was wrong. As we keep going this way, it's going to keep going up this way. So as we go towards negative infinity, it will wind up going up towards infinity. Eventually, it'll wind up going towards infinity, but this will wind up going towards 0. Okay? All right. So we got that one straightened out at least. Exponential growth or decay? Growth, because this part of it is bigger than 1. What's the constant percentage rate of growth or decay? What percent? It is 9% growth. You take 1 minus 1.09, or 1.09 minus 1, I guess. And you get 0.09, and you multiply it by 100 to get it into a percentage of 9%. Okay? Exponential growth or decay? It is growth because this number makes it bigger than 1. It's exponential growth because r is greater than 1. The rate of r is greater than 1. Okay? The constant percentage of growth on this one is 16.3%. Okay. If we're decreasing at a rate of 60% per year, growth or decay? Decay. We have initial value of 15 times, what is 1 minus 60%? 40% or 0.4. So it's 15 times 0.0 or 0.4 raised to the t power. Okay? 15 times 0.4 to the t power. Okay? Our initial population is this, increasing at a rate of this. So it's 465,000 times 1.027 raised to the t power. Okay. Formula for this function. What's our initial value of this? What would the initial value of this be? 3.7. Okay. Now, as you can see, we're growing. So we take 5.273 divided by 3.7. What do we get when we do that? 1 point what? 5.273 divided by 3.7. 1.4. Okay, how many? Round to 3 decimal places. 1.425 to the x power. Okay? So you just have to take the next one down and divide by that one to figure out how much it grew by. All right. Logistic function. Okay? The initial value is 12. The limit to growth is 108. The limit to growth is what you're going to have on the top. Okay? The initial value is not, come on. The initial value is not this value. Okay? So this one is the one that makes sense. Okay? If you put in 5 for x, you should get 42 at the end of it. Okay? Hi, Sophia. Okay? So if you put in 5 here and you throw this into your calculator, hopefully you get 42. Let's just see if we get that. All right. So 108 divided by parentheses 1 plus 8 parentheses again 0.722 raised to the x, close this parentheses now. Oh, not raised to the x, raised to the 5th power. Enter. And it's 42.03, so it's about 42. Okay? Don't use this number here. That's a little trick of the trade. Okay? The 2000 population of a city was 723,000, and it was increasing at a rate of 1.47% per year. At that rate, when will the population be 1 million? So your equation is 723,000 times 1.0147 to the x power. So to figure out when it's going to reach 1 million, on y equals, you put 1 million in for one of them. That's 100,000. Now that's 1 million. And the other one, you put in 723,000 times 1.0147 raised to the x power. And then you change your window. Since this is a million, I'm going to go 1.2 million or 1,200,000. Did I go? Ooh, that's right. And then for my y max, let's say it's going to be 100 years, or not 1,000, 100. And just graph it and see what happens. So, oops, 1 million. Where's my window? Oh, I did the X and Y wrong. I did them backwards. This is 100, and this is 1.2 million. Now if we graph it, there we go. There's my 1 million. There's the one that crosses it. So then you go second trace, find out where they intersect, enter, enter, enter. They intersect at 22.2. So 22.2 years later would be in 2022. That city will hit 1 million. That was at 723,000. Okay? So you got to do a little graphing calculator work, but it's not that bad. Okay. Here's the population in this figure and the time it takes to double. Okay? So, how many years does it take to double? 4 years. From the graph, doubling time for this model is 4 years. The time from 50,000 to 100,000 and 100,000 to 200,000, 100,000 to 200,000 is another 4 years. To grow to that size. Regardless of the population size, it takes twice it takes 4 years for it to double. So I'm missing a blank here. The time required to grow from that to that is twice. Yeah, I think those are the words that I need. All right, whoops. All right. Then it says, use a graphing calculator to solve this problem. A single cell amoeba doubles every 4 days. How long will it take one amoeba to produce a population of 3,000? Okay. So if it doubles every 4 days, okay, we start out with 1. It doubles every 4 days. So the number of days divided by 4, you get double. Okay? Because if it doubled every day, it'd just be 2 to the x. But it doubles every 4 days, so you have to divide the number of days by 4. All right. So we want to see where that equals 3,000. So y equals, we'll put 3,000 in here. And then here, we'll put in 1 times 2 raised to the x over 4 power. And I suppose won't even be able to see that hardly. So let's change my window. Whoa. To 500. Now I should be able to see it. Oh, you know what I forgot to do? I forgot to put in I put in 3,000. Why did I put my window at 500? It should be at 5,000 graph. There we go. There's my 3,000 line. There's my doubling. Second trace. Intersect. They intersect at 46.2 days. 46 days. Okay, now we get to the logarithm stuff. These should be quick and easy. If this equals x, what does that mean? Well, it's 7 to the x power equals 49. 7 to what power equals 49? 2. If this equals x, okay, what's the base of a common logarithm? 10. So 10 to the x equals 10 to the 11th. X equals 11. ln of e to the 5th. What's the base of a natural log? E. So e to the x equals e to the 5th. X equals 5. The ln of e. What's the ln of e? 1. 10 to the log of that. These are inverse functions of each other, so you just get what the log is equal to, 0.82. E to the ln of 4, you get what it's equal to, so then it's 4. Super easy questions here. Then, you actually use your calculator on this one. Type in the log of 0.637, and it's negative 0.1958. 0.196. And last but not least, number 21. Negative 6 plus the log of x. Okay? Compared to the regular log of x, what's negative 6 do to it? What's the negative 6? Basically, it's a log of x minus 6, right? So it translates it down 6. Okay? Okay? So then you would graph what you're supposed to graph on there. Okay? So there you go. There are 21 questions for your sample quiz. I would take this quiz today in class to practice, and then on Sunday, I would do it again to remind yourselves. Okay? So there you go. Dale, you can go ahead and hit the power button on the projector. Hit it twice. There you go. Thank you. Sophia, test. Yeah, I know. No, I'll have you take the actual test now. Because now? Okay.